Welcome back to the swampy yet utterly thrilling grounds of science. I am Professor Zapnik, your favorite messy-haired genius, and today I'm sharing a secret with you that is so fundamental, your morning toast wouldn't even hit the floor the way you're used to without it. But before we dive into the deep end, let me ask a question that is essential for understanding the world. Why is it that you can easily scoop up a tiny kitten, but you wouldn't be able to budge a full-grown hippopotamus, no matter how hard you strain? Many would think it's just pure coincidence. But I'm here to disillusion you. In the world of physics, there are no coincidences. If you're curious about the real answer, first make sure you've watched my video on the first law. There, we talked about inertia, which is the waiting room for today's topic, the fundamental law of dynamics. If you've got that down, you already know that objects are basically lazy. They love to maintain their current state. But what happens if we actually convince them to change their motion? That's where Newton's second law steps in, acting as a sort of mathematical recipe for how to overcome that pesky inertia. Imagine the world as a giant billiard table ruled by three things: force, mass, and acceleration. The essence of the law is that the acceleration of an object is directly proportional to the force acting on it, and inversely proportional to the mass of the object. I know, that sounds like a stiff textbook sentence, so let me explain it more clearly. The harder you push something, the more it speeds up, but the more stuff there is in that something, the harder it will be to get it racing. We physicists describe this with a beautifully elegant relationship. Force equals mass times acceleration. It's important to note that this relationship is exactly true when the mass is constant. Mass doesn't just resist force, it determines exactly how much acceleration is produced by a given amount of force. To understand this better, let's look into my experimental lab. Imagine two shopping carts. One is empty, while the other is crammed with heavy, lead-weighted physics textbooks. If you give the empty cart a firm shove, it shoots off like a rocket because your force is paired with a tiny mass, creating huge acceleration. But what happens if you try to move the cart full of textbooks with the exact same shove and the exact same force? It will barely move. What happened? The force remained the same, but because the mass increased significantly, the amount of acceleration necessarily dropped. This is exactly why a sports car, with its low mass and massive engine power, reaches highway speeds much faster than a loaded semi-truck. This law is the bedrock of modern engineering. This is how we calculate how much fuel a massive rocket needs to escape Earth's gravity, exactly how much braking force a several hundred-ton train needs to come to a stop safely. But let's not stop there. This relationship moves our entire universe. This law explains why a massive cruise ship must shut off its engines miles before reaching the port if it wants to stop, while a small rowboat stays put almost instantly. It's also why it hurts more to be hit by a soccer ball than a ping-pong ball traveling at the same speed. Behind every single movement and every rolling ball, this invisible regularity is lurking. Newton realized that nature doesn't work randomly. If you want to change an object's motion, you must choose the magnitude of your force based on the mass of that object. I hope you can now see the order in the world. Next time you try to push a piano across the room, remember, it's not you. It's just Newton's second law reminding you that mass matters. That's all for today's professorial brain-stretching session. But don't wander too far. We'll soon continue our adventure with the third law, where we'll find out that every slap has a way of hitting back. Until then, experiment wisely, and watch out for those hippos. Goodbye.